Hello, in this video we will talk about real gases and the van der Waals equation. So when we talk about ideal gas, we're making some assumptions here. We make the assumption that all molecules are hard spheres because they can collide off of each other, like we saw in the kinetic theory of gases video. And these hard spheres have mass, but they don't have volume. That's another tenet of the kinetic theory of gases. Also, we assume that gas molecules don't attract or repel each other, which we also previously talked about. And, well, these are actually fairly good assumptions for gas molecules when you're in the ballpark of atmospheric pressure and room temperature. But when you deviate from atmospheric pressure and room temperature, then things start to get a little weird. And so we know that these assumptions we made in the ideal gas model aren't perfect. When you cool a gas, it will liquefy. We've played with liquid nitrogen. And that tells you there has to be some attractive forces between the molecules to hold the molecules together as a liquid. And then these liquids are difficult to compress, which means you can't jam the liquid nitrogen molecules any closer together because they have some volume and they will start to exert some repulsive forces on other molecules nearby. And then quantitatively, we can see this is the case also. So if this were an ideal gas, you would be right on the line here because you're doing experiments on 1 mole of gas. So PV divided by RT should equal 1 if you have 1 mole of gas. And for some gases, like nitrogen and methane, as you increase the pressure, you'll have what appears to be less than a mole of gas experimentally, because the gas molecules attract each other and tend to cluster a little bit and then are effectively behaving like there's less particles of gas. And then at higher pressures for those gases and at all pressures for some other gases, you're experiencing repulsive forces where it seems like you have more gas molecules than you really do because they repel each other and don't want to occupy the same space as much, and that tends to increase the effective volume. Now keep in mind, these changes are over a crazy high pressure range, 200, 400, 600 times atmospheric pressure. So not something we typically have to worry about when we're working with gases close to atmospheric pressure. Now the next question is, what effect do these attractive and repulsive forces have on the relationships between pressure, volume, and temperature? Okay, so the effect of the repulsive forces, that molecules cannot occupy the same space at the same time, is that these molecules will exclude other molecules from the volumes that they occupy. And so this is called excluded volume. And so you can adjust the volume term in the gas law equation by saying that the real volume of the gas is a little higher than the ideal volume of the gas, and they're off by the excluded volume and then the number of moles of gas together, this N times B term. And so the B, it depends on what gas you're looking at, and it roughly depends on molar mass. A bigger gas molecule will have a larger excluded volume that it won't let other gas molecules occupy. And then if you have more gas molecules, you'll have a larger effect. Now on the flip side, the attractive forces, molecules can be attracted to each other to form clumps, which tends to reduce the effective number of gas molecules. So then the gas molecules collide with the wall less frequently, and therefore pressure is reduced. And so the real pressure is a little lower than the ideal pressure, and it's off by this term that relates to a constant A and the square of N over V. And it makes sense that it's related to number of gas molecules and volume, because as the gas molecules are pushed into a closer proximity with each other, they're more likely to form these pairs and clumps. Now this constant A depends on the strength of the attractive forces. If your gas molecule is polar, you'll have a much higher A than if it's a non-polar gas molecule, for reasons that you learn when we discuss intermolecular forces. Okay, so if you put these two pieces together, you get the van der Waals equation of state. It's probably the most famous of the various equations you can use to calculate properties of a real gas. And so we're just making adjustments to the pressure and the volume terms of the ideal gas law. This is still equal to nRT. And so in this table, we list the constants for several gases. The A constant that has to do with intermolecular forces is much higher for ammonia, which is polar, and much smaller for hydrogen, which is a small nonpolar molecule. And then the excluded volume parameter B is much bigger for larger molecules like sulfur dioxide, and much smaller for tiny molecules like hydrogen gas. Alright, so let's do a practice calculation on this. We have a 285 mole sample of nitrogen that's sitting in a 125 liter flask. Let's find the pressure of this gas as if it were a real gas and as if it were an ideal gas. Alright, so let's look at this as an ideal gas. And so PV equals nRT, you've done that before. The temperature, we have to get that into Kelvin, so 598 Kelvin. And then rearrange the equation to solve for pressure. This pressure is equal to number of moles times the ideal gas constant. And now, even though in the kinetic theory video we use the form of the gas constant in joules per mole Kelvin, we need to go back to the gas constant in atmospheres here because we're back to talking about atmospheres as the quantity we're trying to obtain. So use joules when you want energy, use atmospheres or other pressure units when you want pressure. Okay, then we multiply by the temperature and divide this all by the volume, and we find the pressure as an ideal gas is 112 atmospheres. Okay, and here's how to do this calculation as a real gas using the van der Waals equation. So first, the temperature is still 598.15. And now we're going to want to rearrange this equation so we can solve for pressure. So the first step of this is to divide both sides by V minus NB. So then that puts it in the denominator on the right and takes it out of the left side. And then now we can subtract both sides by A times N squared divided by V squared to move that term over to the right side of our equation. And then now this is written with the A kind of floating in the middle and then N squared divided by V squared as a fraction. But whenever you have something shown like this, the A is in the numerator, as is the N. So that means you can write them as both being on the numerator here. All right, moving on. So now we have a crazy plug and chug job. And so here goes the number of moles. Here's the gas law constant, again in liters, atmospheres, mole, Kelvin. Here's the temperature in Kelvin. And then we divide that by the volume, 125 liters. And then the number of moles again times the excluded volume for the nitrogen gas, which you have to look up from a table. And so if you need this number on the test, I will give it to you, don't worry. All right, so there's that term. And then now let's do the second term. So here's the A value, which again we looked up from the table for nitrogen. And then we multiply by the number of moles squared. So don't forget to square the actual number in addition to the unit. And then that's divided by 125 liters squared. Now we just have to compute all of this and see where it takes us. So here's the first term, 122.8 atmospheres, and then the second term on the right is 7.226 atmospheres. Both of these have 3 sig figs if you go through and take a look at that. And then you do the subtraction and you get 116 atmospheres. One interesting thing to note about this type of problem is that it's darn near impossible for me to ask you to solve this equation for volume without having you use a computer. So generally I'll ask you about pressure or the number of moles or temperature, but it's really hard to get you to solve this for volume because it's present twice in the equation, and that's a difficult math task to pull off. So let's compare. So our sample of gas, this nitrogen, as an ideal gas it was 122 atmospheres, as a real gas it was 116 atmospheres of pressure, so there's a difference there. In this case, not a really large difference, but still a notable difference, and if you want that precision, you need to use the correct equation, the van der Waals equation, to calculate for pressure. Now, if we trade the gas to xenon, which has much larger values for the attractive term, A, then our pressure would drop to 97.4. And so in this hypothetical, I'm just putting the word xenon in here and then still using all of the same numbers, just now using the coefficients for xenon. So for different gases, this can be a bigger change between an ideal gas and a real gas, and there's times when that really can matter. Okay, that's what we have for now. Thanks for watching, and I'll see you in class.